How is the weather, Mike, in your part of in the UK?
Well, it's been wet and it's now slightly colder, but we have a 4-day holiday coming up to celebrate the Queen's Jubilee or Platinum Jubilee. They tell me the weather's going to be good for that, which is good because everyone's having street parties.
I will make you jealous if I might. I have not seen a cloud in the last few weeks. I don't know what they look like.
Yes.
Sorry.
Yeah. No, this is okay. We had some good weather and now it's been cold, and then yeah, it should be weather. I mean, I'm no great royalist, but so I will just have to put up with these next 4 days of celebrations. I think the celebration is just because we had to have a queen that lives longer or lives a very long time. But
yeah. How is the weather, Max, in your part of in the UK?
Well, it's been
I'm getting feedback.
It's now slightly colder, but we have a 4-day holiday coming up to celebrate the Queen's Jubilee or Platinum Jubilee. They tell me the weather's going to be good for that, which is good because everyone's having street parties.
I will make you jealous if I have not seen any cloud in the last few weeks. I don't know what they look like. Okay.
Sorry.
Erica.
No, that's this is okay. We had some good weather and now it's been cold, and then yeah, it should be weather. I mean, Paul, I'm getting a repeat. It's recording. With these next 4 days of celebrations, I think the celebration is just because we had to have a queen that lives longer or lives a very long time. But
yeah. Okay. I have a little version.
It's now slightly colder. We have a 4-day holiday coming up.
I'm sorry. I'm live stream issue, but now it's okay. Eric, are you ready? Yes. Yeah. Hello. Good morning, good afternoon, and good evening. So I know it's Australia time is 10 p.m. We are great honor invite Professor Eric Wolanski from James Cook University come here, give us the talk, the dams and climate change accelerate channel erosion and coastal erosion, and particularly in the Great Barrier Reef watershed region. So this is the World River and Delta System Source to Think webinar series. It's co-sponsored by INSF, North Carolina Coastal University, Louisiana State University, State K Lab, Estuarian Coastal Research in Shanghai, and Utrecht University. So before I introduce Eric, as always, in the past 2 years during the pandemic, it's very difficult, challenging time, but one good byproduct, we have this webinar series. So far, we have already 117 talks. All talks have been well archived on our YouTube channel. So feel free to use them for your research and teaching, and also is a copy at the Bilibili station. And so at the same time, you know, next Wednesday, we're back to our original time. Astrid Brom from Delft will come here talk about river response to peak flows and climate change. As I mentioned, Professor Eric Wolanski is a professor in the College of Science and Engineering, James Cook University, Australia. And before that, he has had worked a long time as a lead scientist, senior scientist in Australia Institute of Marine Science. And as you can see, he also he graduated from Princeton University, Johns Hopkins PhD, Johns Hopkins University as civil engineering, and then postdoc at Caltech. He's actually spent a bunch of time in US. His research is mainly from geomorphology and oceanography of coral reef, mangrove, muddy estuary, to the interaction between the physical and biological process determining ecosystem health of estuary and coastal water, oceanic water. So amazing, we know Eric is a well-established, world-known professor scientist. If you look at his citation, Google Scholar is already more than 23,000 citations. At in-text is up to 83. It's a pretty amazing accomplishment. So, Eric, now I'll give floor to you. You can share screen and put the presentation mode. Yes.
Okay, do you see it?
Yes,
Paul?
very good.
I want to thank Paul for all the kind work, and I want to thank all the people who have joined for this talk in Paul's series, which is a really excellent initiative of Paul. I will focus on the dynamics of the Burdekin River and its impact on in the delta and the coast. It's located in northern Australia in the tropics. I want to thank Mr. Chris Canavan, Mr. Chris Hopper, and Dr. Jonathan Lambrex. As an introduction, the food bowl of Australia is the Murray-Darling Basin, which is here. Essentially the overuse of the water and the changing climate, which is the ENSO dependent, and also the climate change have made it an environmental disaster. This is shown in this book, shown here, which is part of a book series that I lead with some of the Mike Elliott on the what we call the ecohydrology of the whole catchment. And we believe that a very similar outcome could occur in the Burdekin River Basin, which is located further north in the tropics on the East Coast. So the next food bowl is planned for the Burdekin Basin in tropical Queensland. It has an area of 130,000 square kilometers with a lot of grazing all over, as well as intensive farming of sugarcane irrigation in the delta, which is shown here. So it is a river which is coming in, goes to the sea. The whole delta is farmed intensively with sugarcane. There is already one large dam which is called the Burdekin Falls Dam, which is located here, and 3 new dams are actually proposed. The dam capture runoff from 88% of the entire watershed. And most of the water is used in the farming of sugarcane, irrigation of the sugarcane in the delta. The dam is 159 kilometers upstream of the mouth of the river. So from here to there is 159 kilometers. I want to point a few features which we understand. So is the river in the delta, the tide go up to here. This is the coast of the delta, with the Great Barrier Reef being further offshore. It flows then into the Upstart Bay, and the over thousands of years, the course of the river has changed, and those sites with the arrow show where the mouth of the river has been a few thousand years ago as it moves around. I want to point also that about the Cape Bowling Green, which is this the spit of land here. There's a lighthouse here, which was put over 100 years ago, and as I will show, there is a strong chance that it will breach here. That will impact another bay, which is called Bowling Green Bay, which has a extensive set of wetlands which are actually listed, the Ramsar Convention. I will show to you there's a risk that it could develop a new channel, the avulsion of the channel, and if that occurs, it will send the channel here in a shorter route to the sea. There are two small towns, Ayr and also so on the north side, and also the Home Hill, which is located here. And that's the scale of the size of this area. I started working in the Vatican in 1920 when I was studying the river, the plume dynamics. And the last few years, I have been using satellite data to look at the coastal erosion. And 2 years ago, some of the cane farmers in the Delta asked me to have a look at what they see as a threat to their life and the livelihoods. And and because I didn't have funding for that study, they helped me, providing me with boats and also four-wheel drive for the field work. Some of the things I'll talk about have been actually published not long ago in a paper with a colleague of mine, Mr. Hopper. So I'll go very briefly. There are a lot of issues with the Burdekin. Post-dam, the whole system of the river is now very turbid. They were clear in the past in the dry season. There have been occasional the event of algae bloom in the coastal water and in the wetland. There's a lot of mud being brought down. I will show some data on that. A lot of it will actually settle along the coast, and it does create a long-lasting turbidity, which can last for months. And the impact, what the hell is that? And the impact of nutrients appear to also enhance the crown of thorn starfish infestation on the Great Barrier Reef. This is a starfish which basically eats a coral polyp. When the dam was built, after the dam construction in 1997, there was an assumption that the delta and the coast were not affected by the dam, and there's been no study with some of the field work which has occurred. It was just an assumption that the dam has no impact. My finding, which I will show you next, in the last 2 years, invalidated that assumption. They are very serious problem, and they are due to changes in the sand flux. So I mined all the available remote sensing data, hydrology, meteorology, oceanography. With some colleagues, we have surveyed the bed of the river. We have also modeled the flood wave in the delta, and the coastal water dynamics, and the longshore sand transport along the coast. Okay, now let's look at some data. With the rainfall, the monthly rainfall, so that's the month number from 1 to 12, is bimodal. There is a wet season in December to March and a dry season the rest of the time. And it varies enormously from year to year. So that's the mean value. And this is the highest which has been observed. There's about 100 years of data. And this is the lowest. Basically, it is entirely zero. The yearly rainfall is dependent on the ENSO and also tropical cyclone. So that's the value here, going back to the year 1948. And you can see that there are enormous fluctuation. It can go from 1,700 millimeter in 1 year and only about 200 in some years. So you got enormous change from year to year. The post-dam evolution of the delta is that the dam has diminished floods from short duration tropical cyclone, but the dam has not changed the flood for months-long monsoon rainfall, like the big flood of 1991. It was basically monsoon rain, which has lasted more than a month. So there is a lot of sand that's coming in the river from the land along the 159 kilometer from the dam to the sea, and as well as sand which is eroded from the bed of the river downstream of the dam as the river tries to re-establish its natural equilibrium, the hungry water phenomenon. And you can see actually the siltation in the delta. Mr. Hopper got all the data. Those are some of the cross section. A, B, C, D, E. I have shown here B. This is the data of the bed level in 2009. This is in 2017. At this point, the bed has come up by 4 meters. And from 2009 to 2017, it has come up another 1.5 meters to 2 meters. Transect D This is the bed level in 2009. This is the bed level in 2021. So again, it has come up. And if you have a look at the satellite pictures during a very low flow event upstream at the gauging station, you can see there is a lot more sand in the river, where you can have water in dry season is now within the channel, which is much smaller. There are two flood relief channels. So if you go near the mouth, this is the main main channel. There are two the flood relief channel, the Anna branch here, and also Groper Creek. We data out of a transect here at the mouth, on this side of the creek. So this is the creek, which is a flood relief. And this is the bed level in 2009 and 2018. And it has come up by about 2 meters. So it is definitely silting. There's no doubt about that. Okay, what's happening? And my flood routing model showed that the flood level have increased from 2009. For the same flood, the flood level has increased by about 1 meter. And this explained the field observation that the flood of 1958, which was 38,000 the meter cube per meter cube per second, had a flood level which was actually about 30 centimeters less than the 91 flood, which had a flood of 34,000 meter cube per second, so which is much less. And obviously, if now the flood level, if the 1991 flood, which was not absorbed by the dam didn't have an impact on that. If that rose by another meter, it would come here, and it will be utterly catastrophic for the delta. What are the consequences of a rise in the flood level? Well, the bank erosion increases. There are cliffs being formed now along the channel, which are quite fresh. They're only 2 meters from the top, from the top of the levee, the natural levee. If the flood water from the next big flood breach, some of the water will flow very freely through the breach, which will very quickly become bigger. The land from here slopes down away from the banks of the river, and this could start the migration of the Burdekin Channel to form a. So that's the point here. In this point here is this point here on the map, on the photograph. It might breach here, and it will form a new shorter channel to the sea. That is, you will have a channel avulsion. And how will this happen? Is that when you flood the land there because of the sand of the old bed of the river, it will create river bubble. It does have the air bubble, which come from the sand and reaches the surface. And those air bubble basically then fluidize the soil, make it very fluid, mud, and that is very easily then moved away. And this will facilitate the new channel. This is what's happening. When you have a spot like that, after it has happened, you form a hole, which can be fairly deep, which makes a waterfall as the flow comes down. And then you can have a whole series of those holes, like you see here. And it forms a new channel. So it can happen very quickly in a few hours. We know that this type of process, the channel erosion, occurs at the large river at a speed which is typically 10 to 15 kilometers per day. If this occurs in the delta of the Burdekin, it would be catastrophic for the human livelihood and the economy, because it will cut off the highway and the railway, not by a small channel, but with a channel which could be 1,000 meters wide. So we believe that this abortion is a process which is originally entirely natural, which might occur every 1,000 years ago or so, but because of the dam, it may now be accelerated, and it could occur very suddenly in one large flood sometimes in the future. Let's now move to the coast. So here's the river, is the mouth, and here's the coast going to the Cape Bowling Green. So we are looking at this site here. So those are all at the old mouth of the river, a few thousand years. This is Cape Bowling Green with a lighthouse here. And this is what we observe. The coast is starved of sand, and it is now it is now very rapidly eroding. The rate of erosion along this side here of the tree edge is 4 meters per year. And it slowed down because of the roots of the tree. Even if the tree is dead, it still has roots which help to hold the soil together. But if you go at sea on the coast, the rate of erosion is much higher, 25 meters per year for the sand along the beach. So it is very rapid. So I went through all the data. What do we know about Cape Bowling Green? We know that it did exist when the Captain Cook first came. He just showed a point on the map. The next good map is in the year 1927. It shows the tip here with the site of the lighthouse in the year 1927. And there's only a very tiny the sand spit, maybe 200 meters long, north of the lighthouse. The 1948 military map, here's the lighthouse. It showed there was a bridge actually south of the lighthouse. After that, I have data from 1961 to 2004 survey, government survey, which took picture every 5 years of the coast. The first picture is in the year 1961, and that bridge was entirely plugged. And then in the last few years, we have a lot of pictures from satellite, the Googlers, the Sentinel, and also the QuickBird. So we know that historically, this system recovered after storms, like after the breach of 1948, because there was a lot of sand that came with the river in a river flood. But now at this point, a breach is developing. This is a view out of satellite in 2011. There's a scale here, 80 meter. So that's the width here. In 2020, that's the width here. So it has become half of the length of a tennis court. So here's a good view. You have a lot of mud bank inside of the bay. There's some mud even now on the seaside, and some part here along the coast don't have any sand at all, and you got mud bank along the coast, which you didn't have before. The sand has been washed, and if you walk along, you can see lot of erosion along the banks, along the coast. All the trees north of the lighthouse are dead. So there is intense erosion. If you go outside and you look at what's happening, you can see that during a storm in very recent years, storms have gone on top of the sand dune, and they brought in all sort of debris from the sea, which had then overtopped the dune. So it's starting to breach. So this is all the data that we have with discharge, which, as you see, is just a few peaks. Floods last most time less than a week. So that's the discharge, the main discharge per day. That's the discharge. That's the main discharge for the year. That's the mean sea level nearby, in the port of Townsville. That's the mean sea level observed with satellite altimetry. The main wind is a wind from the southeast. Oh, I go back to this picture. This is a plot of the wind as an histogram in 1990 and in 2020. And you can see that the wind from the southeast really hasn't changed much. There might have been a small shift in the wind direction, but there's no big change in how often the wind blows from the southeast. So that's the plot of the mean wind from the southeast. This line indicates when the dam was built. It goes back to the year 1948. This is how many the windy days there are per year. At next to the Cape Bowling Green, we have got a lighthouse. We have got a station which takes data of the wind, and I took the wind from the southeast with a speed which is the 7 meter per second as a day, which is windy, because that's the speed where the wind waves start to move the sand. And it seems, although it does vary from year to year, it seems to go up in time. So that plot started in the year 1948, and it goes up to now. And that's the width at the point where a breach might occur in the Cape. So it went up as the speed grew over time. And then from the year 2000, it seems to go down. So what we can infer from that is that in the past, the peninsula was supplied with sand the pre-dam. Post-dam, the sand supply, seems to be insufficient, that it cannot maintain. And this is exacerbated by mean sea level rise and also the wind change. And the bit north of the lighthouse seems to be basically in a terminal decline. It's going down since the year since the year 2000. It's looking like this. I want to point out very briefly that the trend of a increasing number of the windy day and of a rise in mean sea level occurs all along the coast and at sea. In terms of the wind, it does not occur at those two reefs, but at all the other side, the windy day plot here, the side from here down 1,000 kilometers south, we see that rise in the number of the windy day, and the mean sea level is definitely also going up at all the sides along the coast, at all the ports. From all the data, we have done a sediment budget. For the fine, you got something like probably the 6 million ton per year of mud, which is flushed out, but it doesn't stay trapped in the delta. For the sand, we had what's coming in the dam, in the reservoir, we have 354,000 tons per year. What's going past the dam is only about probably the 17,000 tons. So most of the sand is trapped. The sand is coming from the side, and sand, which is very coarse sand, which is being picked up from the bed of the channel in those 159 kilometers. And that might be 120,000 tons per year. We don't know how much sand leaves the delta to go to sea. What we know is that from the growth of the peninsula is that the sand transport is along the coast. So that's mainly with the wind-driven wave, because there's no swell, because of the reef, is of the order of 93,000 up to 160,000 tons per year. So to understand what would happen, we have done the modeling of the water current with no breach and with a breach. If the breach is small, that's what it looks like. We can also map the turbidity front between the clear water at sea and the water in the bay, which is quite turbid. That is observed. That's observed with a quick bird satellite, and thus we get out of the SLIM model. It's a fair match. We use a sand transport model, the brochure, which is based on the current and the wind-driven waves. So there's a sand flux which is being limited to a very small narrow band, and it becomes faster once you go past this point here, where there's a change in the slope of the coast. And so we ask ourselves, what will happen to the Bowling Green Bay on the Ramsar side if it's breached? The side is quite healthy, but it's not untouched. It's already impacted by the tailwater from the farms. And so we have used a SLIM model to understand that. We were focusing on focusing on the dugong, which is a sort of manatee, like you have marine turtle, the fish, the crabs, and also the water birds. So we know that most fish and crab that live in the bay spawn in the coastal water, and if they want to then recruit back into the estuary, the preflection fish larvae need to remain within a few kilometers of the estuary so they can swim back. So I've done those studies to see what would happen to the fish larvae. So this is the plot of the fish plume when they were still at the preflection. That is, they are entirely passive. That's what it looks like over up to this number of days. They can start swimming on the day number 14. So this is where they are. If there's no breach, if there's a small breach, if there is a full breach, and so if they were entirely passive, this is where they would be. If they swim, you can see that all those fish larvae here will move in and move in the estuary, and a lot. This is. And a lot of those fish larvae here also, you can see there's a hole there now, have a chance to actually recruit. So, and there's no time to go in that. That's what happened with the wind. There is the annual the spawning aggregation of the black marlin. We know that from tags have been put that they spread from Cape Bowling Green, which is the only side along the coast where those fish come. The other side are in this area on the reef instead. So this is where they spread in the southern New Guinea, in Vanuatu. And the risk from a breach then for the black marlin is the loss of those sharp fronts at the tip of Cape Bowling Green, where those fish they come together to feed on the bait fish, the herring, which come out of the wetland in the bay. So I'm at the end of the talk. I'm on time. There are insufficient data, but with the data that we have, it shows that the channel in the delta is silting, and quite likely we will have a channel avulsion. The whole peninsula is right now the whole peninsula is right now eroding. A breach is developing, and the coast is starved of sand since the dam was built. The channel, if there was a channel avulsion in the delta and a breach of the peninsula, all to a large degree due to the dam, it will be disastrous for the people living there and for the environment. I cannot answer the question I was asked by some farmer. in the possible paths of the new channel in the delta, will I be killed by it? And very clearly, in my eyes, channel abortion cannot be called an act of God anymore, and it can be fixed. And there is a urgent need to stop to spend a lot of money, hundreds of thousands, in all sorts of reports, engineering reports, which are desk-based, with a consultant not even aware of the severe bank bank erosion, like the one that you see here. And then I can see that, but so there is a lot of science that needs to be done. It is a very serious issue, and it shows that dams need to be managed to basically maintain the flux of sand. And it's a very difficult question. How do you do that? And what can you do to then avoid the channel abortion, and to also avoid the breaching of the spit of the peninsula? Thank you very much.
Eric, thank you. Eric, thank you very much for this wonderful talk. So because this area for many of colleagues in the community is not familiar, but now we know, we learn a lot. So to the audience, if you have any question, you can just unmute yourself and directly ask Eric. Jim, go ahead.
Thanks, Paul. Thanks, Eric. That was a fascinating talk. So many things in there. I had two questions. One, can you clarify for me, what's the cause of the siltation on the delta? Because the sand flux is decreased due to the dam. So why is there siltation and a grading bed level if the dam has decreased the sand flux?
That's because there's still sand which is coming in, both being picked up from the bed of the river in the sloping area near the dam, and also which is coming from the land over the 159 kilometer.
Right.
And since we don't have the big floods, have been are not so big anymore, then that sand stays in the delta because there's no slope.
Okay, so it's basically just those lower flows that are not getting there, that aren't reworking that sediment. So linked to that, on one slide, you said that the probability of the avulsion or the chances of avulsion had been increased since the dam had been there. I was just wondering what the potential mechanism for that is, because again, I'm just wondering why dam construction would actually increase the probability of the avulsion. Again, is it linked just to the fact that you've got the decreased probability of the lower flows?
Well, I just see a lot of erosion of the banks. I assume it's simply because of the dam effect. The flood, even if they are smaller, they last a lot. They last a lot longer. The base of the bank is then wet for is then being wet a lot longer, and since the bed has also come up a few meters, then the flood level, even the flood is smaller, has also come up. Does that explain, or you're not clear?
Yeah. Okay. Yeah. No. I just think about what that link was. For the increased bank erosion from the fact again that you had less sediment coming in because it's been stored upstream of the dam. So I suppose in my mind I'm just unclear about what's causing that aggradation that can then actually increase the potential for avulsion. But yeah, thank you for the answer.
Okay. You're welcome.
Okay, anybody else? Any more questions? Yeah, Mike.
Okay, thanks, Paul. You can see me there. A great talk as ever, Eric. As Eric and I have discussed many times, I'm interested in the repercussions of these things. And Eric's point about it not being an act of God, and we've seen this several times now, that the more we know about a subject, the less anyone could say, no, it's an act of God, it's nobody's responsibility. So the question, Eric, is where would the liability, if you were trying to address a lawyer, where would the liability lie? Would it be with the owners of the dam, although presumably the anything that was said when they did an EIA of the dam when it was built 35 years ago would deny that this could happen. But where would the liability lie? Would it be the owners of the dam, or would it be the local landowners or the upstream landowners? Who if the farmers wanted to find someone who was responsible, who would it be?
I don't know the law, Mike. Like we had big the flood in Brisbane 10 years ago.
Yeah.
And they came from a dam which to keep the dam safe, they had to let a lot of water, but they stored water in the dam as much as they could, so that when the rain came, it just made a big flood. So
yeah,
this was a case of a man-made flood, and it has been in the court ever since. So for the last 10 years, it has been fought in the court. Is it an act of God, or was it the mismanagement of the dam? When you have got a lawyer, they can find a lot of argument either way.
Yeah, as we've seen, I don't know if listeners will remember, but certainly the Australian film about an act of God, where the fisherman tried to sue God or sue his representatives on earth, which is the chief rabbi, and it's a good film for these sorts of lessons. But I think Eric shows the problem we have, and it's exactly the same problem with climate change. The more we know about climate change, the less we can call it an act of God, and therefore someone or something is responsible for it. The only problem is getting someone to admit responsibility. And of course, it's the little people that suffer. It'll be the farmers that suffer within this, but they shouldn't have to be paid. So yeah, it's a really good case study.
But by the way, I've seen that Dr. Webb, the Greg Webb, is a participant, and since Paul has a lot of interest to hear more about the impact of climate change on the Great Barrier Reef, I would like to suggest that certainly Dr. Webb could give a really fantastic talk at this series. Are you still there, Webb?
I'm here. Forgive me, I'm in my pajamas and bathrobe, but I'm here.
Okay. Well, it'd be good if you could, if you could give a talk about what is the impact of climate change. You have 500 years of data. It'd be fantastic.
Yeah, I could probably do that at some point. I'm actually a little bit overwhelmed for time in the next month or two.
Well, we can definitely do in the fall, in the maybe September.
Yeah, I might be able to do it then.
Yeah.
Yeah, I'm pretty flushed. And sorry, I'm just coming off. I've had one of these bugs that's going around, so I can't talk very well today either. But
okay, we will.
Yeah, I'd be happy to give a talk on new geochemical evidence from corals and microbialites, looking at water quality related to climate in the GBR.
Okay.
And so forth. We have some nice new data.
That would be fantastic. So, okay, we keep in touch. You know,
Yeah,
Eric, I
no
have a
worries, Eric.
question. Yeah, Eric, you know, a couple weeks, 3 weeks ago, a colleague from Ocean University of China, Dr. B, gave a fantastic talk about the Yellow River, the management of the reservoir of the water flow, because of the dam have almost cut off all flow from the large Yellow River. But they have a kind of similar problem as you present. Even the Vatican is not the large river, but is a large river locally. But you know, still the impact of the dam is similar, because particularly the silt, the sand accumulate on the channel, and so what they did, you know, they create some artificial flow peak. That flow peak is kind of able to deliver, to wash more sediment, you know, from the channel to the delta and to the ocean. So that's a great way. I mean, it's a try. Not sure it's the best way or not, but is any discussion in your local region to artificial manipulate or some kind of release some water from the reservoir?
We could not do it in the Vatican because it doesn't have any gates.
Oh, okay. That's okay. That's a little bit, yeah, different.
Yeah.
That's so.
Can I just ask Paul? I mean, based on that, Eric, it would be really interesting to go back to when the environmental impact assessment was done for the dam, and there will have been done because it was only 35 years ago. It would be really interesting to go back to the EIA that was done and just see whether they predicted anything like this. And your last comment about not having gates in, they must have taken the view that they would never need to release the pressure, release the water, so they weren't going to build gates into it. And that's why they have these what do you call it? These the Anna branch and the other creek as a relief channel. But it would be really interesting to see what they said 35 years ago, and whether anyone thought of these issues. And I'm sure they didn't, but it'd be interesting to see what they did say, see what the consultants at that time said about these.
Yes, it'd be nice to go back in time, but we are all really quite busy people.
Well, that's Mike. You raise a very good point. Actually, a group of people should write a review paper or report. Let's see, go back, look at original dam design or environmental impact assessment, and you know, let's retro back. You know, look at the back and what we learn from today's point of view. compare the original, design or report. I mean, that's something.
It's a good point, Paul. This is one of the problems we have with environmental impact assessments, that after they've been done, usually nobody goes back and says, did the consultant really, did what they predicted, was that right? And if they got it wrong, is there any comeback? And we never do that because, of course, if they got it wrong, then nobody is going to destroy the dam afterwards. We don't go back.
Oh, that's very good. Okay, we have a question, Nathan. Yeah, go ahead.
Yeah, thanks. If I could just offer a little bit of information further to Mike's point about, has someone gone back to look at the EIS from a water quality and a limnology perspective on the floodplain. It's interesting, the consultants concluded that the dam and the water in the dam wouldn't be turbid. There was enough groundwater in the catchment to suppress the turbidity. The dam would remain clear. In 35 years, the dam has gone clear maybe once or twice. It's persistently turbid because of the nature of the soils and lack of groundwater. And what that's done is when they pump the irrigation water from the dam across the floodplain, there's 1,000 kilometres of distribution channels. This water's turbid. And the floodplain was seasonally ephemeral. It was clear, and now it's persistently turbid water, full of nutrients. The entire limnology has changed. So, Mike, you're right. The consultants did get it wrong, and from an environmental water quality limnology, they got it entirely wrong.
That's very good. Well, maybe a couple of people here can maybe have a very quick review paper, just to have a case study, in this area, in this watershed and other river system. That would be a very good starting point. So look at what is wrong, what is right, 30 years, 35 years ago.
Yeah.
That's good. So actually, 2011, the big flooding in Thailand indicate the dam, the reservoir lost the function to control flooding. Particularly, we have a long-lasting rainfall. The reservoir already full, and they cannot hold any water, store water. They have to release extra water plus the extra rainfall. That's make the downstream much worse. The case in many small, Cambodia have a similar problem a couple years ago. So that's something we really need to look at back.
Yes, it'd be good if there was somebody who had the time to look at them, to have a look at all those case studies of dams around the world and what they do to floods and the coast and the delta. It'd be worth it. Yes.
Very good. Okay, I think we are already 1 hour, and I think Eric, thank you very much for this wonderful talk and also the very constructive discussion here. And again, this talk is also archived on our YouTube channel. If you like, you can always go back to rewatch it and recommend it to your student or your colleague. If no other question, thank you, Eric, again. We can stop here. And for some colleague, I'll see you next week. Okay, thank you.
Bye-bye.
Bye-bye.
Thanks, Eric. Bye. Bye.
Bye-bye.